In this video, we are going to study sign reversing involutions. So sign reversing involutions is a common technique in combinatorics to prove an identity involving sign. So let me give you a precise definition. So a sign of a set x is just a function. It's a function which I denote as gn function from x to the set of +1 -1. So that's a simple function. And a sign reversing involution on x is an involution. Say phi from x to x such that the sign of phi of x is minus sign of x for all x in x except the fixed point of phi where this fix of phi means the set of elements are fixed by this involution, like this. Okay. Here an involution means that its inverse is itself. So if you apply phi twice, then it's going to be the identity map. So that's what an involution means. Okay, so a sign reversing involution is an involution satisfying this condition. So for fixed point, of course you cannot change the sign because fixed point is x is the same. But if x is not a fixed point, then this image of x has a different sign than the x itself. So if we have a sign reversing involution, then we can say something like this. So if phi is a sign reversing involution on x, then we can say that x for all x in this set x, if you add the sign, then this is the same as the cardinality of the fixed point. So this is actually quite easy to see, but let me explain this using a diagram. So suppose that x is here. This is whole set is x. So involution means that for every element it sends something, but if this gets sent to something else, then this must be sent back to this because it's an involution. So every involution actually looks like this. So we have like fixed point set of x, phi. So here every element just gets sent to itself by the map phi, but if it's not a fixed point, then we have two parts. Something here it gets sent to this, and this sent back to this. So this is kind of an bijection. So we have two parts here, and a phi will send everything from here to some element here and vice versa. So and oh, I think I forgot to mention one thing. Here I think I have to mention one more thing. We may consider more general case, but I think it's more common to have this condition. So such that we have two conditions. all x for the first and second. Sorry about that. Sine of x equals 1 for all fixed points. Okay. Yeah, if we actually it's fine that if we delete this, then we can, instead of this will be just sum over all x in fixed point sine of x. But if we have this condition and this is just everything is 1, so we can say something like that. All right, so but let's see why this identity holds. So let's say element here, element say here a has sign +1. Then elements here will have is minus sign, right? -1. And if this has minus, this has plus, but we can always move elements with plus sign here in this side, and then elements with minus sign in this side. Then we can say that everything here has sign plus, everything here has sign minus. And of course, a fixed point has plus sign. And then because of this sign reversing involution, this +1 will be cancelled with this -1 and etc. So here, this is basically +1, sums of +1s and -1s, but -1s are all cancelled with part over here because of the sign reversing involution, and we are only left with the fixed point. So this is why we get this identity. And using this sign reversing involution, we can prove identities involving signs. And a typical example would be this, the simple identity, but let's prove this using sign reversing involution. So k from 0 to n minus 1 to k, and choose k equals 0. So this is actually a simple consequence of the binomial theorem, but we will prove this using sign reversing involutions because we want to see what sign reversing involutions are. So in order to prove an identity like this using a sign reversing involution, we need to construct, of course, a set, and we have to define the sign, and we have to construct this sign reversing involution so that this becomes exactly this. So in this case, let's say x be the set of all subsets of n. This bracket n means integers 1 to up to n. We will use this notation often. And we have to define the sign. So for an element a in x, define the sign of a to be -1 to the cardinality of a. Okay. And we want to construct sign reversing involution with no fixed point. So okay, we want to find a sign reversing involution on x with no fixed points. Why? Because then we can apply this theorem, this identity, and this is empty, so it's going to be 0. But here, the sign, this is exactly this, because there are k elements, n choose k elements in x, which have sign -1 to the k. So in this case, we will get something like this. X is in a, but maybe I use a is in x, sine a, this means a is in a, -1 to the a. So if a has cardinality k, then we can sum over k from 0 to n, because cardinality can be anything from 0 to n, and then the cardinality of A is k, so minus 1 to the k, but there are n choose k elements A whose cardinality is k, so this is equal to this. So the left hand side becomes this, and the right hand side becomes 0, if we can find such a sign reversing involution. Okay, so now we will construct a sign reversing involution. Actually, it's not that hard. So for a subset of n, define phi of A to be just this symmetric difference, A symmetric difference with this set containing only 1. Here, A symmetric difference B for two sets A and B basically means A cup B minus A cap B. So in fact, so if you know, using the Venn diagram, a triangle B means this. And in fact, in other words, we can write in this way. So there are two cases. If one is in A, we just remove A. And if one is not in A, we add 1. So in any case, we have one more element or one less element. That means the sign will always be changed because this is changed by plus or minus 1. Then phi is a sign reversing involution on X with no fixed point, right, as we desired. Any set or any element, it cannot be sent to itself because of this construction. So yeah, this is an example of using sign reversing involution to prove an identity like this. All right, now let me give you another example. So in the previous lecture, we learned this identity. We proved this identity, k from 0 to pmk, pnk, a to the k, k factorial equals e to the a to the n over n factorial delta nm, where p and k is the Charlier polynomial, right? So it's k from 0 to n, x to k, maybe I should write this in the general case, x to k minus a n minus k over n minus k factorial. So we proved this using generating function. We consider like g x comma w summation w to the n, and we did a little bit of generative function manipulations to prove this. But we can also prove this using sign reversing involution. So let's prove this using sign reversing involution. So first, to do this, we will rewrite this, considering this as a formal power series in A. But let me rewrite this formula. So left hand side over here, let's say this is star. So left hand side of star equals, so I'm just putting this definition into this. So the summation k is still there, and for the summation for this, I'm going to use summation index I. So I is from 0 to m, and this is x is k now, so k choose I minus a to the m minus I factorial, and summation j from 0 to n, k choose j minus a to the n minus j over n minus j factorial, and we have this vector there. Okay, and we will let me rewrite this, and I'm gonna collect all the summations first in front. Okay, and this is k choose m minus I minus a to the I over I factorial. So I'm gonna replace here m, so because I is from 0 to m, you can replace I by m minus I, right? Then I is still from 0 to m, so this will become I, this becomes m minus I, just a change of the indices. And also j, I'm gonna replace j by n minus j, then we will get k choose n minus j minus a to the j factorial, a to the k factorial. And then we're gonna collect all the terms of a to the fixed power. So we're gonna have capital N from n and a to the capital N over n factorial, and then we will see what quantity appears here. So because if you multiply these three vectors together, it's going to be a to the minus 1 to the I plus j, and a to the I plus j plus k. So we have to have these three indices ijk, I plus j plus k equals n, right? And the sign is minus 1 to the I plus j. And because of this, I'm gonna multiply n factorial, capital N factorial, and I'm gonna collect these denominators. So I factorial, j factorial, k factorial, and finally the two binomial coefficients, m minus I, k, n minus j. Okay, and here we are gonna assume that, say, R choose S equals 0 if S is less than 0, because here, you know, I is from 0 to m. So if I is bigger than m, there's no term like that. So we will, by convention, we assume that if this is negative, term just vanishes. Also same here. So the left hand side can be written in this way. Okay, so we want to show that this is equal to this. So it's going to be 0 if n and m are different, and this is equal to the single term like this if n is equal to m. So basically we want to understand this. Okay, so to do this, let's look at what this is. So first fix n, and then summation this. Let me copy this formula, and then we can rewrite this in this way, equals summation a comma b comma c in. So this by the way, this is this can be rewritten in this way: a multinomial coefficient I, j, k. This is basically the number of ways to select I elements and then j elements and k elements from n. It's like a binomial coefficient, generalization of the binomial coefficient. And this is in x minus 1 to the b minus a, c minus a. Here, where x is the set of triples, such that if we combine them, or if you take the union of three, I forgot to mention this, triples A, B, C, this is the set n, capital N, 1 up to n, and A has cardinality k, B has cardinality m, C has cardinality n, and B intersect C minus A is empty. Okay, so now let's see why this is true, and I'm gonna explain that using a Venn diagram. So we have A, B, C, and A, B, C, their union is n. So that means we need to put these n integers into the regions divided by these in this Venn diagram. So we have 1, 2, 3, 4, 5, 6, 7 regions. So we want to put them there, and so that's this condition. And this condition means that we need to put k elements there inside A, and but before we put B n elements and n element, we will first put a k element here. Okay, maybe I can explain this way. K, maybe like big here, k element, and here and B minus A minus B is this region, and but I think it's easier to explain this first. So this is empty. That means this is B's unions, B intersect C, and we subtract this, so we get this part. This part is empty. So this is empty. Let me put this first. So this is empty. So we have k elements here, and we put here I elements. Okay, here I elements, and j elements here. This is j. So in total we have k, I, j. They are all disjoint. So in total they must have n elements, right? So this is the number of ways to distribute this into this region and this region and this region with cardinality k, I, j is exactly this. So this is how we divide this into these 3 regions that I marked there. And then this means that we want to put here, we want to place, we want to put m minus I elements, and we want to put n minus j elements there, and in this way. Okay, then because this has I elements, this has m minus I element, this is empty, so B will have m elements, and similarly this has n minus j, this part has j, this is nothing, so C will have n elements in total. So that, and the sign of this, right, and then for A, B, C in this set X, define the sign function to be that thing over here, minus 1, 2, this. Then by the construction, this B minus A is here, this is I, and C minus A is here, which has j elements, so that's exactly this. So this is basically the signed sum of the elements in X. So let's say maybe this is star, double star. So the left hand side of the double star equals sum over all ABC in X sine ABC. So we want to find sign reversing involution so that at the end we get something like this. So that's the plan. And in fact, the sign reversing involution is not that difficult, but let me draw the Venn diagram again. Okay. This is A, B, C. We know this is empty. And let me put this, let me say some region number. So this is region number 1, this is region number 2, this is 3, region number 4. Let's say, let's give some names to these 4 regions. And now the sign reversing involution will be defined in this way. So for ABC in X, define the sign reversing involution ABC in this way as follows. So first, case 1. One of these regions, ABC, 1, 2, 3, 4, is non-empty. All empty, let's say that's a fixed point case. So case 1, all regions 1, 2, 3, 4 are empty. In this case, then define phi ABC to be just a fixed point, so ABC. In this case, we don't change anything, okay? In case 2, otherwise, at least one of 1, 2, 3, 4 is non-empty, okay? In this case, we will find this element. So case 1, case 2, let S be the smallest element in 1, 2, 3, 4, all of them. So consider all elements in these regions and take the smallest element there, smallest integer. And then of course this S will be one of these 4 regions. It can be either 1, 2, 3, or in 4, okay? And then move this element, this integer S, to, okay, there are four cases, okay. I think I'm gonna copy this so that we can still see the full diagram. Erase this part. So if S is in region 1, then move S to region 2. Then if S is in region 2, move it to region 1. If it's 3, 4, then move it to 4 or 3, like that. That means if S is somewhere here, just move this there. And so that means we change this the sets A, B, C, D a little bit. And after this, let A prime, B prime, C prime be the resulting sets. Okay, then define phi A comma B comma C to be A prime, B prime, C prime. Okay, so this is the definition of our map phi defined on X, and this is a sign reversing involution. Why is that? So first recall that the sign of ABC is -1 to a minus, was it a minus b? Yeah, b minus a. B minus a plus c minus a. So you see, the fixed point, of course, nothing changes, but for in this case, sine ABC equals minus 1 to b minus a, c minus a, right? So that means it is not minus 1 to the number of elements here, region 2 and 4. But the number of elements in region 2 and 4 will always be changed by plus or minus 1 because of this construction. Because if S is here, it will be moved to this. So this sign, this exponent will be decreased by 1. But if S is here, it will be there, so it will be increased by 1. And same here. If it was here, it will be out of region 4, so this will be decreased by 1, and if it was in 3, it will be moved to this region, so this will be increased by 1. So always this will be increased or decreased by 1. So this is always minus 1 to b prime a prime c prime a prime, which is exactly minus sine of a prime b prime c prime. So it changes the sign, and it with fixed points like this. So by the sign, so that's thus v is a sign reverse involution on x. And what is the fixed point? So fixed points are those in this. So fixed point is like a, b, c in x, such that no elements in 1, 2, 3, 4 regions. That means, so this is nothing, this is empty. So that means b is always only here. So b is here, and same for c. C is here, but this is empty, this is empty, this is empty, so C is here. That means B must be equal to C, and that is also inside A. So B equals C, and that is inside A. So this is just, these are the fixed points. So therefore, we can say that sum over all A, B, C, sine of ABC equals the fixed point. I don't need the like this. But let's count how many elements in the fixed point. So this is all we need to do is to count A, but A, so A in this case, suppose if B equals C is in A, then A union B union C is just A. So this is the whole set 1 up to n. So we don't have any choice for A. So A is completely determined. So all we need to do is to decide these elements. But B equals C, and they have cardinality. Where is it? N, M, or N. So this can happen. This can happen only if M equals N, because this is the cardinality of B, this is the cardinality of C. If M and N are different, this can never happen. So that means it's a fixed point. There's no fixed point. But in this case, if M equals N, then the fixed point, the size of this equals number of ways to select N or M, they are the same, N elements from this capital N. So this is going to be capital N, choose N. So in summary, we can say that this is N choose capital M, capital N, delta Mn. This is what we have discovered so far. But then let's go back here. So we just found a formula for this. This is equal to delta m and choose n, right? So we can replace this by this, okay? So then, therefore, summation, the thing that we started with is this formula. And this is summation n 0 a to the n and factorial delta mn and choose n. But if you compute this is delta mn, and this the sum is for all capital N, but we will only one term. Oh no, sorry. You can rewrite this if you, because this part is n factorial cap n minus n factorial. This is just a simple computation. You can just immediately get that this is e to the a to the n over n factorial. Yeah, if you use this and then cancel this and then factor out this thing out in front, and you will get this formula. So this is what we wanted to prove right here. So we prove this using sign reversing involutions. Okay, this is more complicated than this, but the idea is basically the same. We construct a set S x and define the sign of each element in x, and we construct a sign reversing involution on x. And so that's the proof. And we will see in this semester many examples like this using sign reversing involutions.